Whoa, all of a sudden it's way zoomed in.
On me?
No, on the display there. Yeah, I wasn't accounting for the fact that the movie view is narrower than the, all right. It is recording now, yes.
Isaac.
Yes. Welcome to your last virtual class. Yeah, or you can be in class forever now, right? Yeah. Whenever you want to be back in college. Yes. So, I just keep seeing that same lecture over and over again.
Don't they force anything new?
I know, that's right, yes. Okay. So, sky maps to power spectra. So, this is from a very nice talk that was given at the 2004 AAS meeting. And so the idea is that we've got the hot spots and the cold spots, or what the author is calling peaks and troughs. And these are cartoons representing what if you had just a very large peak and a very large trough? What if you had kind of medium-sized peaks and troughs scattered around? What if you had cute little tiny-sized peaks and troughs scattered around? It's related to what we were saying before. What would the power spectrum look like? Well, if you had just one peak and one trough, it's pretty much all that L equals 1 in that case. Here is kind of a cartoon of what happens if most of the power, if you will, most of the significant coefficients in the expansion in terms of YLMs are for around L is equal 10-ish. Here's for L is around 1,000-ish. So exactly how the power spectrum varies with L tells you something about typical sizes of variations in temperature, how big the spots are, angular size, on the sky. So, meanwhile, we can understand what's making the spots of various sizes in the first place by thinking, okay, these were these sound waves in the early universe with really low periods. So for example, what we call the first peak is one that went through one cycle of compression from the Big Bang to the time of recombination. So in other words, it went through, it went through half a cycle in 380,000 years. That is subsonic. It's below the frequencies your ears can hear. So these are sound waves, but they have spectacularly low frequencies that we're talking about. But they're still sound waves, just very, very long wavelengths, slow, long period sound waves. The idea is that it was this complicated pattern, but remember that you can take any three-dimensional distribution, any function in 3 dimensions, and Fourier transform it, write it as a sum over plane waves, essentially. And so you can think of that complicated pattern of sound waves in the early universe as being composed of plane waves of different wavelengths and corresponding frequencies in the early universe. And like all self-respecting sound waves, and even ones that don't respect themselves, the longer the wavelength, the lower the frequency, the longer the period. So large-scale fluctuations have longer times to oscillate through a full cycle than small-scale fluctuations do. So this is supposed to represent time, and this is supposed to be corresponding to the value of the redshift, where we went from radiation-dominated universe to matter-dominated universe. And when the universe was radiation-dominated, when radiation ran the show, the sound waves weren't able to form yet, because radiation-dominated sound waves are as a result of compression and rarefaction driven by pressure and gravity. And if radiation is dominating everything, you can't build sound waves if the photons are saying, no, we are dominating, you're not going to be able to compress yourself because the radiation pressure is just too high and running the show. So at the transition to a matter-dominated universe, that's when sound waves can start to form. when regions that are slightly denser can start to collapse because of their gravity. Regions that are slightly less dense start to expand because they have less gravity, and so other stuff pulls away that material. And so this is supposed to represent a big blob, which is big enough that by the time of recombination, when the photons are free to fly, so that we kind of see a snapshot at recombination. The sound waves stop at recombination because at that point, the universe has become transparent, and so as a result, photons are no longer trapped inside the gas, and they don't contribute air pressure to it anymore, and also the universe is transparent, so we see the sound waves at the time of recombination. Here's one that's large enough in scale that it has only started to compress a bit by the time of recombination. And so as a result, it's not going to contribute very strongly because it's not going to be at a particularly hotter or colder temperature than average. But here's one which is of just the right size and therefore just the right frequency of oscillation that at the time of combination it has managed to get itself to the point of maximum compression before it was about to turn around and start expanding again.
You said these are blobs?
Yes.
Oh.
So, go ahead.
I'm just confused. Like, are they like isolated from the rest of stuff?
No, see the thing is, you have to think of this in terms of, there's this very complicated function, the pressure and density are very complicated functions of position and time in all these waves. And so I mentioned you could Fourier transform and write it as a bunch of plane waves, okay? But here, you can also, in some rough sense, talk about, well, here's a region which is large in scale that is falling together. So these are not well-defined blobs or anything like that. It's more like, here's a region where it just so happens that it's pretty coordinatedly falling together and it's about this size. That's what I mean by these blobs. It's not that well-defined a thing. It'd be more precisely do it in terms of plane waves, but that's harder for people to picture, I think is what it comes down to. So here's a blob that goes through one, and actually the stuff we see on the sky corresponds to more like regions like this. There were blobs of various sizes that went through various amounts of compression and rarefaction by the time of recombination. This one manages to compress itself maximally just before it was going to rebound at the time of recombination. And so it's at maximum temperature, and so it'll make a strong spot on the picture we make of the CMB, because here's a kind of maximally hot spot. Here is one that's a bit smaller. It has reached maximum compression and started to rebound before recombination, so by the time recombination happens, it's neither maximally hot nor maximally cool, it's somewhere in the middle. So blobs of this size don't show up very strongly because they're just kind of in the middle of hot and cold, maximum emitted compression by the time of recombination. Here's one that fully compresses and then fully expands by the time of recombination. And so the idea is that we see peaks in the power spectrum at values of L that correspond to blob sizes that have managed to go through either one full compression or a compression and a rarefaction or a compression and a rarefaction and a compression. In other words, we see blobs most strongly, we see the most strong contribution for L values such that those blobs manage to be at either maximum temperature or minimum temperature at the time of recombination. We've caught them at a moment when they're either maximally compressed or maximally expanded. And because blobs of different sizes vibrate at different frequencies, the time of recombination, 380,000 years, picks out blobs of certain sizes, namely ones that after 380,000 years are going to be caught at either maximum compression or maximum expansion. And so this is a qualitative plot of CL, the expansion coefficient, versus L, really you have to add it for all the different M values, make something that's a combination of them. So the idea is, here's a peak corresponding to blobs that went through one cycle of full compression. Here's, and this is the sort of the main peak in the spectrum, the first peak. The second peak corresponds to smaller blobs that went through a compression and then an expansion. And down here would be another one where you had compression, expansion, compression again, and so forth. So you get a series of peaks corresponding to blobs that had just the right size, so that 380,000 years was a magic time for them. We either caught them in a moment of biggest expansion or biggest compression, highest temperature or lowest temperature. Yes?
When it's talking about the contributions to like the CLs from the Doppler and the adiabatic, what does that mean?
I don't want to. So yeah, I know. So there's there's a contribution to what we see that is a combination of the temperature of the blob. So when it's maximally compressed, it will be at its hottest, and when it's minimally compressed, when it's maximally expanded, it will be at its coldest. Mitigating that somewhat is gravitational redshift. A blob of maximum compression that is hottest also has the strongest gravitational field, so the photons that climb out of that well undergo a redshift as a result of that, and so there's competing effects. And furthermore, when the blob is moving towards us or away from us as a result of expansion or contraction, that produces redshifts and blue shifts, which also show up as a temperature change. So in fact, what we see is a combination of how compressed or expanded it is and how fast it's moving towards or away from us as a result of being in the middle of contracting or expanding. So you actually have to combine those things in order to get the overall effect that you see. So here, notice that Doppler is a minimum. The Doppler effect is a minimum for maximum compression or maximum expansion because at that moment the blob is not moving. So there's a so in other words, you get an adiabatic contribution that's referring to the temperature. So this is a peak in adiabatic because it's hot, so it makes it look hotter as a result of all of that. It's a minimum in the Doppler contribution. So the total contribution, you have to add the temperature variation effect plus the Doppler effect, the redshift and blue shift, because the redshift and blue shift shows up as a change in the temperature as well. So actually I'm glad you asked that, it made me explain that. So the net effect is when you combine them together. But the biggest effect, as you can see, is the adiabatic effect overall. The peaks correspond to the peaks in the adiabatic effect. And whether the blob is hotter or colder because it's compressed or expanded. Yes?
For the CMB, do you have an idea, or does it make sense to say how big those peak blobs would be?
Well, I am glad you asked that. Let's start showing plots. Yeah. So I'll just jump ahead and I'll jump back. Right? Look at this. These are predictions of what the spectrum would look like for different shapes of the universe, whether it's flat or spherical or saddle shape, and for different proportions of what percentage is baryonic matter versus what percentage is dark matter, and so forth. Because as I'm about to explain, you can infer how much dark matter there is compared to baryonic matter from the relative strengths of the different peaks compared to one another.
So that's going to affect the Doppler part.
It's gonna, okay, so I'll explain it here. Okay, so here's the idea. Gravitational modulation. So, and I know you can easily read that from where you are, so I'll read it for you. Influence of dark matter modulates the acoustic signals in the CMB. After inflation, and by the way, these, and so here's the amazing thing. So inflation was this exponential expansion in the size of the universe when it was very, very young. You think about 10 to the minus 30 seconds old, might have been associated with something like a strong force breaking off from the other two forces other than gravity, that sort of thing. Although we're confident that inflation happened, we don't know exactly. There are lots of models for inflation, for something that would cause there to be a very strong cosmological constant for a very short period of time in the early universe. But the idea is that inflation would magnify microscopic quantum fluctuations to macroscopic size. And those magnified macroscopic size quantum fluctuations become the seeds of structure formation later on. So when we look at the clusters and superclusters of galaxies throughout the universe, what we're seeing is, we now believe, what that represents are gigantic scale results of microscopic quantum fluctuations before inflation that then got magnified and continued to get magnified as more and more matter fell into denser and denser regions. So talk about microscopic effects having a microscopic phenomena having a macroscopic effect. The large-scale structure of the universe we now think represents the frozen-in quantum fluctuations before inflation, which is just mind-blowing. Okay, so influence of dark matter modulates the acoustic signals in the CMB. After inflation, denser regions of dark matter that have the same scale as the fundamental wave, the one that has the largest peak in the spectrum, the one that went through one compression cycle before recombination, represented as troughs in this potential air energy diagram. So here they are represented as essentially a plane wave. Pull in baryons and photons by gravitational attraction. So, in other words, there's more dark matter than baryonic matter. The dark matter, then, is more effective at concentrating itself gravitationally, and that